All right, good morning, everybody. My name is Manya Ghobadi. I'm an associate professor at EECS department. Every computer we have today, every mobile phone, every digital watch uses transistors, digital transistors, to operate. What I want to talk about today is a jump in technology, a future where we use photonic, where we use light waves to perform computation, as opposed to using transistors. But why do we want to think about a jump in technology and light? Machine learning is taking the world by storm. ChatGPT is the fastest growing application. In just 1 month, just last January, ChatGPT had 600 million live inference queries from 100 million unique visitors. Do you know how long it took Instagram, for instance, to capture that many users? 2 years. So already ChatGPT and generative AI have had disruptions and innovations in search, content delivery, code generation, and whatnot. And we all know that there is massive implications for systems and networking research areas. I want to argue that there are two important metrics for machine learning systems. First, latency, and second, energy consumption. In terms of latency, we do need to build systems that are able to train machine learning models quickly. On top of training, we also need to build systems that are able to provide inference results for these systems. From an energy perspective, though, ChatGPT's monthly electricity consumption is in the millions of kilowatt hours. An average American home's energy consumption is orders of magnitude lower than this. Taking training and energy consumption even on the side, the consumption of serving inference queries can dramatically and very quickly become higher than training. So this is very, very important. And my argument is we need fast and energy efficient machine learning systems. So how do we go about this? Traditionally in systems, we tend to throw money at the problem. We tend to put a lot of servers, buy a lot of GPUs. It seems like what today's hyperscalers are trying to do. But we can't answer the energy consumption problem with just money, with just throwing compute resources at the problem. So my argument is that we need to rethink the way that we are performing computation. And I want to talk about using photonic for machine learning inference. So what is photonic computing? Literally what it means is to use light waves to perform computation in the analog domain, as opposed to in the digital domain. In fact, computers were born analog. In the 1800s, Charles Babbage conceptualized computers as analog devices. And even back as 1985, there were ideas and demonstrations of using optical devices to accelerate AI. Why is this interesting? Why should we start thinking about using light waves? There's so much potential. There's a lot of papers that show that photonic devices can perform computations at hundreds of gigahertz frequency. Think about the frequency of a CPU on your computer. You could look it up right now. It's probably a few gigahertz. Transistors are unable to perform fast operations because of this fundamental limit of clock frequency, whereas light does not have that fundamental limit. Literally, the device reacts to light as opposed to having a clock signal. There's also papers that shows that the energy consumption of performing computations in the optical domain is extremely energy efficient at 40 attojoules per operation. This is great, this is fantastic, but think about this. Photonic computing has never really gained practical traction. Why? Why is that? We knew this, we knew the fast computation, and we also knew about the energy efficiencies of photonic computing for a while. Let me tell you the basic fundamental working of a photonic computation operation, and then you'll see why we haven't really been able to build systems, practical systems with photonic computation. The picture here, what I'm showing, is a device called a transceiver. This device is just yay big, It's very cheap. It's a commodity device in data centers today. What this device does is that it takes digital data and translates them into optical light for communication. The entire internet is basically based on optical communications. We take our data, our email, and then optical lights and optical fiber cables carry our data. So how does this device work? If you just break open the little device, what you see is that there is a laser, and then there's a device called the optical modulator. Okay? The job of the optical modulator is to modulate the signal, the digital signal, into photonic light waves. Okay? And so on top, there's digital data, say the content of your email, for instance. It's coming into this device. There's a laser, creates a carrier light, and then the modulator performs or modulates the carrier signal. So by definition, the process of modulation is basically a multiplication, if you think about the Fourier transform of the signals. Okay? So we have defined this process of modulation. We've been using this throughout the lifetime of the internet and throughout the lifetime of data centers. So now, here's what I'm going to do. I'm going to add a second modulator right after the very first modulator, and I'm going to feed another vector of electrical data to this device. Now again, based on the definition of what optical modulation is, the carrier signal, which is now the new modulated light, is going to be multiplied by the applied voltages. And so what we have here is a double modulated light where the amplitude of every wave is actually the multiplication of the digital data. In real life, it's proportional, it's not exact. And Einstein has showed that this proportionality is fixed and can be calculated and can be calibrated. But for the sake of simplicity, I'm just showing you exact. So what am I going to do? I can collect this light using a photodetector or a capacitor, and I can just send out the result back to the digital domain. So what did I do? I performed vector-vector multiplication or vector dot product without using any transistors here. Okay, great. And like I told you, these modulators can be very fast. The one that I'm showing you can buy it for, say, $30, can operate at 15 gigahertz already. So what's the problem? The problem is that these devices are passive. There's no external signal like an ALU, for instance, to say perform operation. It's literally a material. The device we're using is lithium niobate. That's modulating light all the time, whether it's noise or meaningful data. And so it's really hard to control these optical devices, to send the signal and say, start operation right now, send me back the results so that I can curate the data. That's basically the problem, or that's basically the challenge with these photonic devices. They're passive. Let's take a very simple example and see why, even for a very simple example, this challenge is significant. What I have here is a very simple neural network. On the left-hand side is a handwritten number, say number 6. And on the right-hand side, the neural network just tells you what is the number. Okay? Even such a simple neural network has multiple layers. In this case, it has a few layers that are performing ReLU or softmax. They're performing some nonlinearities, okay? But even for such a simple neural network, there are some operations that can be performed in the optical domain and some operations that cannot be performed in the optical domain, and we have to bring them together. Okay? So this is in systems lingo, we call these DAG, a DAG of operations. And as a result, we need some form of a control signal to understand where the data comes from, where to feed it into these optical devices, how to get the result, how to clean it up, and then get it ready for the next layer of operation, and so on and so forth. So the implication is that the way that we are building these optical systems is sort of like a stop-and-go system. So we end up coupling this control logic very deeply into the data plane operations. For instance, imagine that there's a ChatGPT packet, and we want to use that packet to understand it and then perform the inference in the optical domain. So the system needs to process the packet, then ask the controller, what should I do? Maybe the controller says, well, you need to flatten the packet. Afterwards, the controller might say, okay, now this is the time to perform the multiplication and accumulation in the photonic domain. Then the system would ask the controller again. The controller says, okay, perform the digital accumulation into the digital domain. Sometimes you have negative data, and then you have to go back to digital domain because it's almost impossible to represent negative numbers with light. And so there's like some cleaning up, data cleanup, and some non-linearities that we have to go back and forth between the digital and photonic domains. And this coupling of the controller really slows down the whole system. Imagine you have a Lamborghini, but you don't know how to drive. What would you do? Maybe what you might do is look at the driving instructions, and then it says, okay, put the gear into gear one, and then look back at the instructions and it says, okay, now give it a little bit of a steering wheel, and then change the gears. And we don't drive like this, right? You have to give it gas and then stop and read the instructions. We actually learn how to drive and then drive with our muscle memory. This is what's happening, though, with the optical systems. We tend to keep asking the controller, what's the next step? What should I do? What should I do? So that's the stop and go operation. Let me show you exactly the manifestation of this stop and go. This is an experimental platform of a lot of science and nature papers that show significant improvements of photonic computing systems. But what they end up doing is that they have maybe like a Python interface. This is the controller, the brain. And then there's these massive devices that are hundreds of thousands of dollars. And these devices are basically performing the wave and then changing the digital data into optical domain. And then they feed the data into this sets of photonic modulators and photodetectors, get the result using expensive oscilloscopes, go back to the controller. The controller looks at the data, decides which layer of the neural network the data is, whether or not nonlinearity should be applied. And so coming back and forth between this sort of loop. And the implications is, if you only look at the photonic piece, the system is fast and energy efficient. But if you take the end-to-end latency, several orders of magnitude difference between what's happening here and what's happening at the very end-to-end. For the consumer, for the user, the end-to-end is what matters. When I'm submitting a request, I'm expecting the response to come back. I don't really care whether the computation piece was fast and then everything else was slow. Same story for energy. Yes, the energy consumption of the photonic piece is very small, but then all these other devices need power. And so it sort of defeats the purpose of building a photonic device if you're unable to seamlessly integrate the control system into the data plane. And that's basically what we do. We co-design the photonic and digital systems together, and we basically have a programming abstraction that enables programmers to have a photonic computing system without really getting the controller into the data plane. So the trick is that we install our abstraction at every level of computation before performing the operations. And then we basically get rid of the controller logic. It's kind of like the driving example. It's like now it's a muscle memory for the data plane. And then we let the data to go through the data path without really having to stop at every layer that it needs to make a decision. So now the question is, what should this abstraction be? It can't be as complicated as a Python program because then we're back to the same problem. But it should also be powerful enough to capture at least neural networks and computation of, say, layer after layer inference, for instance. Turns out that there is a very simple way to thinking about this abstraction. What we call this abstraction is a count action. Remember the neural network that I showed you a couple of slides back? What was I doing? I had, say, 300 multiplications followed by another 100 multiplications followed by maybe 10 additions. Neural networks are perfect for this. The sets of operations are already predefined. And so you can capture this based on the architecture of the neural network, and then program the entire data path based on perform X many number of multiplications followed by Y many number of additions, and so on and so forth. So we install this count action abstraction into the data path, and then we program it based on the neural network architecture. And then afterwards, everything can just zip through. I'm not going to go to the details of this, but just a very quick example of we can use this count action abstraction to even synchronize the data very simply by just counting the number of valid signals. Let me zoom up, putting everything together. What we have built so far is a network interface card that takes packets from the internet, curates them and processes them, then feeds the data into these photonic computing cores, and then takes the results back, performs some nonlinearities, and then continues with this operation layer after layer, and then finally spits back the results. Here's a photo of our testbed. What you can see here is that on the left-hand side, we have an FPGA for performing the digital computations, and on the right-hand side are our modulators and photodetectors here. I'm going to show you folks a video, a very short video of how this system works. But one of the results that I'm showing in the video is about accuracy. How accurately can you even perform, say, multiplication or vector dot product? And so it turns out that photonic multiplication is pretty accurate, or at least accurate enough for machine learning models. And so here what I'm showing you, and I'm going to show you in the video in a couple of seconds as well, is we select some random numbers, 8-bit fixed point numbers, and then we multiply them using this system. We also multiply them using transistors. And then we're plotting the results on this figure. And we show that the accuracy is pretty good, actually, for ML systems. Okay, let me show you folks the video. So what you're seeing here is on the right-hand side is our FPGA shell. And so we're just loading the Linux kernel here into the FPGA to bring up the system. And then we have a Python interface to program the system. And so we're using a Jupyter notebook to program our FPGA. Now, the very first step that we perform is called calibration. Remember back in a couple of slides, I told you that the proportionality of the results is actually, the results are not exact, and Einstein showed that there is a proportionality. This is what we're doing. We're just computing the proportional ratio so that every number can be calculated back and forth between digital and analog domains. It's a very simple and fast step, but it is required at the beginning. So now, let me just multiply two numbers, 0.7 and 0.9. I'm expecting to get 0.63. Okay? As you can see, initially I'm just loading 0.7 into the system, and I'm just going to read it back. I'm not going to multiply it first. So I loaded 0.7 in a digital domain into my optical system, and I'm reading it back. And you can see I'm reading it roughly at 0.71. It's good enough for machine learning, actually. Now I'm going to feed 0.9 into the system and read it back. You can see I'm reading 0.93. And here's the multiplication. As you can see, I multiplied the two numbers right back to back, and I'm getting 0.63. What did I expect? I also expected 0.63. And now finally, I'm going to just select a bunch of random numbers and just multiply them the same result that I showed you in the previous slide, and then plot the accuracy of multiplying in digital domain versus in the photonic domain against each other. You can see the accuracy is even better, 99.9% in this setting. So looking ahead, I'm envisioning that a world where there's a seamless integration of efficient systems to transcend the boundaries of computation. Systems not only optimize machine learning training or inference, what I think is that systems are going to foster interpretability, scalability, and all ethical considerations. And I'm thinking that machine learning systems will become intuitive collaborators to augment human potential in addressing complex challenges for diverse domains. With that, thank you for your attention. I'm happy to take questions.